Hello, my name is Josh Bergen and I am the president of Precision Machinery. You can find more about us at www.pgmr.ca. Precision Machinery is located in Western Canada. We have been servicing the sawmill industry for the last decade and have a large presence across North America. Cox saws are distributed in the southern US and Chematic Technologies in Australasia. While we provide other manufacturing services and equipment, saw guides and their maintenance has been a primary focus for us over the years. In addition to saw guides, Precision manufactures molds, manifold alignment systems, and CNC guide dressers. We've also just released our new Kaiser equipment line, which includes a fully automated version of our popular CNC guide dresser and a fully automated disposable knife grinder. The focus of this presentation is saw support and cooling. Some of the most overlooked components in mills are saw guides, yet they are critical for the accurate and efficient manufacture of lumber. We think nothing of regularly changing anvils, chip segments, knives, and other wear components to keep them in good condition. At the same time, we struggle to maintain our saw guides, even though they operate in one of the most violent areas of our sawmill. We demand tight tolerances on our saws, but overlook the components that support them. There are many times I've heard, "We can't afford to replace these guides right now," or "We just bought new guides last year, we need more," or something similar. Saw guides are no different than saws, knives, or anvils. They are a consumable item, not a capital component, and we need to change the way we think about them. Let's review what saw guides do. First, some nomenclature to ensure we are using the same terminology. The most critical area of a saw guide is the clamp surface, often referred to as the head or heel. The body is the part of the guide the babbitt pad mounts to. Lubrication galleries in the guide feed an air-oil-water mixture to the pocket of the babbitt pad. Lands around the outside of the babbitt pad are machined before each guide change to provide fluid film support for the saw during operation. When discussing guides, you will often hear the term thou. Often we forget how small a thou is. A thou is 1/1000th of an inch, 0.001 inches, 25.4 microns for those working in metric. A tenth is a fraction of that again. A tenth is a machinist slang or an abbreviation for 1/10,000th of an inch. It is 4 decimal places, 0.0001 inches, or 2.54 microns. To put those numbers in perspective, a human hair measures around 4/1000th of an inch thick. The thickness of that hair exceeds our total allowable saw clearance, which I'll explain in more detail in a moment. If we split that hair into 4 equal pieces, each piece will be 8/10ths or 20 microns thick. That number is roughly the tolerance our tradesmen need to work within to maintain proper saw support. So how do we ensure that tolerance? Well, it's not easy. If you went to any technical training institute and told them you needed to maintain a half-thou tolerance, they would say you need a temperature-controlled environment, dust control, hairnet, and even maybe a smock. The fact that our tradesmen come close to this is a credit to the profession. Even so, there are things we can do to ensure we maintain tolerance. We work in an incredibly dusty, dirty environment. You can't walk across a mill without something dribbling on you. The first thing we need to do is maintain a clean work environment. Proper tools and workstations are important. Regular, detailed inspections are important. While most mills do not have an inspection room like this, you should have a granite block, micrometer, and dial indicator with a proper base. We go into a lot of saw shops and often find these basic inspection tools in disrepair. Each year, we find an average of 2 to 3 inspection blocks that are worn out, unknown to the mill. Micrometers are often out of calibration and give false readings. Dial indicators are the wrong graduation or not present. These tools should be readily available for use on a daily basis. If you have to dig your granite block out from under other equipment, it is likely your guides are not being properly inspected often enough. Upkeep. We often find guides like the ones pictured here in use. When the guide can no longer support the babbitt pad, when the internal galleries are damaged, when the mounting surface is in disrepair or bent, the guide needs to be removed from service and replaced. Guides can be made from a variety of steels or aluminum. Aluminum has become very popular in the past years as a lightweight alternative when design and application allow. A special finishing process called anodizing can be done to aluminum guides to extend their life. There are two main types of anodizing you will see in the sawmill. The first is Type 2. It is available in a range of colors, including black. This type of anodizing is popular for most consumer aluminum products you see, such as bicycles, electrical components, automotive parts, etc. Coating thickness is usually less than half a thousandth of an inch, or 13 microns. The other anodizing is a Type 3 engineered hard coat. Coating thickness is around 2 thousandths of an inch, or 50 microns, if done properly. I should note that this is the only type of anodizing we use, as it is vastly superior to anything else available. Maintaining tight tolerances is easier with proper equipment. We have a highly technical machine shop that produces hundreds of saw guides every month. We understand what is required to maintain tight tolerances. I can give one of our tradesmen a machine that is 20 years old, and he'll be able to produce an acceptable guide. But if I give him a well-built, modern piece of machining equipment, he will be able to do the same job faster, more reliably, with less stress, and above all, with a better tolerance. Our lumber mills are running higher feed speeds, thinner saws, and more production than we have ever done in past. Additionally, we are doing it with less manpower. Where we used to get away with one guide change, we are now doing 3. Where 2 thou deviation ran acceptably, we now have a problem with saw life. Accuracy matters, and we need to give our tradesmen the proper tools for the job we expect. Let's discuss saw support. Here is a typical guide stack. A common tolerance for saw plate is +0 -1 thou. Some mills demand +0 -half a thou. Those are very tight requirements for a saw, and if we're going to expect that tolerance, we really should look at the tolerances for the rest of the support structure of that saw. The first support surfaces for the saw are the babbitt pads. These pads are formed at the mill, bolted to the guide body, and then machined to size. They must be parallel to the clamp surface and flat. Let's quickly review basic guide theory. Here we have an end view of a double arbor machine. We can isolate one arbor, or guide stack. If we look at a side view of that guide stack, we can see the guides, babbitt pads, and saws. When we machine the babbitt pads on a guide, we are creating a control surface for lubrication to support the saws during operation. Here's how that support mechanism works. Conventional pad design theory involves a machined surface, called a land, around the pocket of a babbitt pad. During operation, lubricant, usually a mixture of water, oil, and air, is pumped through internal galleries into the pocket. The pocket fills and lube is forced out onto the guide lands. The saw runs on a film of lubricant radiating outward from the filled pocket. Be aware that this theory is out of date, but because it is still widely accepted, I include it here. I will come back to this later in the presentation. Now that the babbitt pads are machined, we have essentially created a flat bearing. Basic bearing principles apply. Saws should never contact the machined babbitt. As with any bearing, clearance is critical. On the screen are 2 guides supporting a saw. When we machine guide pads, we want a clearance of 1 to 1.5 thou between each pad and the saw plate. That means we have a total saw clearance of 2 to 3 thou. That's the sum of the clearances on both sides of the saw. Remember, our 4 thou thick hair, our total saw clearance is less in thickness. Our total tolerance then, or allowable machined deviation, is plus or minus half a thou. Again, going back to earlier in the presentation, that is equivalent to an average human hair split in 4 parts. Ideally, saws want to run in a straight line. Poorly machined pads can result in the problems you see in this picture. Excessive clearance leading to loss of lubrication, poor alignment of the saw causing increased wear and reduced runtime, point loading, and saw binding. Misaligned saws lead to lumber deviation, increased guide wear, increased saw damage, shorter run times, and increased saw changes. So what checks should we be doing to our saw guides after machining? First, we should be checking the machined width of our babbitt with a micrometer. A fun fact about micrometers, they are only considered accurate to about 1/1000th of an inch, due to human errors in measurement. We can achieve better, but only with accurately high-quality tools as well as proper training for each team member. An interesting test, have all your tradesmen independently measure the same part to 4 decimal places and see how much variation you end up with. When we check machined width, we need to inspect multiple points around the land surface, ideally near a mounting screw. Total deviation should be a half thou or less. This deviation is a function of your milling machine and pad design. Next, we need to inspect the machined surface for flatness. Just because two surfaces are the same distance apart or parallel does not mean they are flat. Proper inspection requires a granite inspection table and dial indicator. You need to sweep the entire perimeter of the machined pad or land area. Total deviation should be a half thou or less. 3/4 of a thou is allowable on larger guides. Now that we've briefly reviewed guide pads, we can look at the next critical support surface. The clamp surface of the guide must be accurate. When new, this is a function of manufacturing. For used guides, wear and damage can cause issues. First thing is to inspect the clamp surface for damage. In the picture you can see where burrs and damage to the clamp area have had to be honed off over time. I personally like to take a small straight edge in good condition and gently run it over the surface to check for high spots. Any raised areas can be gently and carefully taken off with a honing stone or small file. Be careful not to take off more than necessary. Proper handling and storage of your guides will reduce damage. Also, proper manufacturing techniques and coatings will make maintenance easier. You'll note the colored guide pictured is not properly anodized. You'll also note it does not have proper edge treatments. Inspecting the clamp surface of the guide is similar to inspecting the guide pad. Using a micrometer, check multiple points around the surface of the heel. Total deviation should be a half thou or less. As with the guide pads, parallel does not mean straight. Guides can be bent over time or improperly manufactured. Inspection is done similarly to the guide pad. While the picture here shows inspection of the guide pad, the setup to check the clamp surface is the same. The surface of the heel, not covered by the retaining clamp, can be checked for deviation. Total deviation should be a half thou or less. Remember that the closer you can imitate the clamping of a guide in the sawbox, the more accurately you will be able to inspect your guide. To give you an idea of what we commonly find with older equipment, I've attached part of an inspection we did for a sawmill in Western Canada. This particular machine was running steel guides that had not been replaced in 5 years. The mill thought the guides were fine, but the steel showed signs of wear, and we worked with the saw shop staff to inspect each guide in the machine. In the chart above, you will notice we captured a great deal of basic guide data. There are 2 items of interest I want to highlight here. The first is the weight of steel versus aluminum, because it is a question I commonly get. In this machine, the steel guides each weigh 22 pounds, or 10 kgs, and these are not large guides, as you can see. The same guide in aluminum would weigh 7.5 pounds, or 3.4 kgs. To do a full guide change with steel means moving just under 400 pounds, 180 kgs, of guides. Those guides have to be moved to the machine, in and out of the machine, back to the saw shop, and through all the necessary babbiting, machining, and inspection procedures. A full set of aluminum guides, by comparison, would weigh only 134 pounds, or 61 kgs. That's a substantial reduction of workload. The second item I want to draw your attention to before moving on is the time required to machine a full set of guides. Here you have average cycle times of a precision guide dresser versus an older machine, an IMW in this case. As with most of these older machines, the heads were not stopped between cycles, even though work-safe rules would never allow exposed, rotating heads of that size. On the precision machine, the heads of course come to a complete stop after every cycle. In addition, they are completely enclosed. What I wish to highlight is the machine time. The older unguarded machine took over 3.5 hours to machine a full guide set. The precision machine took just under 13 minutes for the same number of guides. But back to our guide report. The part of this inspection I want to highlight is the measurement of the clamp surface which locates the guide. As you can see, brown cells are below accepted tolerance, gray cells above, and white cells are within spec. Very few guides passed inspection. To make these numbers a bit more clear, I've graphed them here. What we should be seeing with properly toleranced guides is the yellow and orange lines between the blue and gray lines. Obviously, that is not the case. In fact, you can see that several guides are above the gray line. Wear and usage makes guides smaller, not thicker. Some of these guides were never manufactured properly and were out of tolerance from day one. The second thing we checked was the straightness of the clamp surface. Remember the parallel versus flat note earlier. In the detail above, you can see that almost all the guides had excessive deviation, either from wear, damage, or mismanufacturing. When looking at the clamp surface of a guide, we have to consider stack tolerance. Let's take a guide, manufactured to a proper tolerance of plus or minus 2.5 ten-thousandths of an inch. At the top of a 10 guide stack, we have a possible deviation of plus or minus 2.5 thousandths of an inch, or 5 thou total. In a 17 guide stack, like the one pictured here, the total potential deviation at the top of the stack could be plus or minus 4.25 thousandths of an inch, 8.5 thou total. This is one of the reasons why accurately manufactured and maintained guides are so critical. And now we should talk about spacers. I understand why mills want to use spacers. It is an easy way to increase your guide inventory for a percentage of the cost. There are several problems with spacers. In our experience, most spacers are not manufactured to a tight tolerance. Often they are torch cut plates. If they are properly manufactured, they tend to get more abuse than the guides. I was in a mill recently that used spacers. Those spacers were on a shelf of the guide cart and were installed after the Babbitt pads had been milled. The spacers were rusty, so I knew they were out of tolerance already. I saw the spacer pulled out of the pile, and yes, it was a literal pile of parts, wiped on a pair of pants and bolted to the guide. Let's look at how spacers affect stack tolerance. First, let's assume we have a spacer manufactured to the same high tolerance as a guide, plus or minus 2.5 ten-thousandths of an inch. Let's also assume that spacer has been installed with no foreign material between the mating surfaces, and the bolt pattern is such that it properly retains the spacer on the guide. Finally, let's consider there is only one spacer on each guide, rather than two, as I've seen in some assemblies. At this point, we still have our guide tolerance to add in, at plus or minus 2.5 ten-thousandths of an inch. Now at the top of 10 guides and 10 spacers, we have a potential deviation of plus or minus 5 thousandths of an inch, double our previous measurement. At the top of 17 guides, we have a potential misalignment of plus or minus 8.5 thousandths of an inch, or 17 thou total. The takeaway? Spacers often cost more than they save. We've reviewed the necessity of maintaining the clamp surface. The final component of guide alignment and saw support takes us to the guide manifold, the part that locates the guide stack. Over the years, we have found many of these manifolds out of alignment, often caused by damage or inaccurate line boring, as they are a function of the guide post. Here I've depicted a typical vertical double arbor from the top. Let's consider that there are two potential directions for misalignment, which I've labeled here as perpendicular or parallel. In most situations, we can find a combination of the two. On the left is a top view of my VDA, on the right an end view with the cat traveling into the screen. As you can see, this type of misalignment will produce tapered or wedged boards. Parallel misalignment generates different problems. The saw itself makes a wedge-shaped cut, causing mismanufactured lumber. More importantly, if the angle of misalignment exceeds certain parameters of tooth side clearance, excessive heat, saw damage, and guide damage will result in reduced run times and increased repair work. To give you an idea of how critical this is, a 22-inch or 560 mil saw with a new tooth will start to experience issues when the manifold deviates more than 10 thou per foot, or 0.83 millimeters per meter. Where we used to be able to accept some misalignment, we no longer can. Thinner plate sizes at higher speeds with increased production requires a more accurately located saw. The level of the guide manifold is often a direct result of the guide post alignment during manufacturing. Over the years, we tried several methods to align guide posts and the manifolds attached to them. What we found was that we could level the saw stack without having to level the guide post. At Precision, we've designed an adjustable manifold that can replace your existing design. It allows us to level the guide stack and subsequently the saws independently of the guide post. Some highlights of our prismatic alignment system include 100% component contact. Our system does not rely on bolt tension to maintain level, eliminating problems caused by the cyclic action of clamping, impact from debris, or bolt stretch over time. The system is Precision produced and owned. Your mill deals direct with the supplier, engineer, manufacturer, and installer when working with Precision machinery. No middlemen. We have the experienced professionals. Our techs and engineers regularly work with the guides, guide machining, saw box levels, and lubrication. We understand why a guide must sit level and properly support the saw. Precision can level the manifolds on each end of the stack when necessary. The press, or clamp lock, is often overlooked during alignment, yet it can have an effect on total saw support. That covers saw alignment, though while we are on the topic of guides, we should discuss advances in saw cooling. I reviewed earlier conventional pad theory, how lubricant is supposed to fill a guide pocket and radiate outwards around the entire land surface. In Western Canada, we have a scientific research organization called FP Innovations. We wanted to know if the industry's conventional lubricant supply theory was accurate. We found it was not. For simplicity, think of the rotating saw acting like a pump. That pumping action wants to draw fluid from the reservoir or pocket of the babbitt pad. Depending on the direction of rotation and the shape of the pad, only certain areas of the support land receive proper lubrication, limiting the effective support and cooling area. In addition, the pocket experiences only a partial fill. The question then was, is there a better pocket or pad design? Several gallery and pocket designs were tested. The design that was eventually settled upon was what we refer to as a teardrop. Rather than supplying lubricant to a pocket, we direct flow to the top of carefully designed guide lands, feeding them directly. In this drawing, you can see there is no bottom land. That is because lubricating the babbitt pad this way eliminates the need for a conventional pocket. The bottom land is still optional. To date, we have manufactured molds with and without it and have found no measurable difference. We leave the top land on to protect the area from debris. Here is some of the supporting data. A saw box was loaded with saws and conventional designed guides and pads. Temperature sensors were put on the saws. The gang was started and a cant ran through. It took an average of 80 seconds for the saws to cool back to their pre-cut temperature. When the same saws were run with a teardrop design, the cooling time dropped to 7.5 seconds. Its finest saw temperature increases uniformly during cutting, and we don't wait 80 seconds between cants. What this test showed us was the extreme improvement in lubricant delivery to the saw. With tighter environmental regulations and increased costs of lubricant, being able to reduce usage and saw damage is critical. Please contact us if you wish to have a copy of the full report. The final proof for this new design is in a real-world example, which we have permission to share. The first conversion in North America was completed at a large West Fraser mill nearby our facility. The mill asked us to redesign and update their gang to the teardrop system. Before the conversion, the mill was changing saws once each shift. After conversion to the teardrop, the mill went to one saw change every 4 shifts. The mill was so pleased with the improvement, we recently converted all of their remaining saw systems to the teardrop design. Precision offers complete guide services. That includes saw guides, molds, CNC guide milling machines, adjustable guide manifolds, inspection services, and vendor management. For more information on any of these items, you are always welcome to talk to us directly. If you are in the southern US, you can also contact Cox Saw. No matter where you are, we are always happy to help. Thank you for taking the time to listen to this presentation.